Welcome to Lecture 11, where we continue our discussion of Karnaugh maps. In this lecture, we'll learn or begin to learn how to use Karnaugh maps to simplify functions, and in fact to write them as simply as possible. I like to give students a set of guidelines, or maybe you might even call it a recipe for how this can be done. And so the first step in the recipe is to identify rectangular groupings of one cells. These groupings must contain a number of one cells that is a power of 2. Start with the largest groupings and proceed to smaller groupings. Remember to never include a grouping that is entirely contained in another grouping. I'm sure that probably doesn't make a lot of sense now, but in just a few moments as we begin to look at examples, I believe it will. So, after you have identified the groupings, and by the way, for grouping, I'll go ahead and say grouping equals a prime implicant. So I might as well use the more traditional term for that. These groupings that we will identify are the prime implicants. Now, after we've identified all the prime implicants, the next step will be to identify all essential one cells. Now, what is an essential one cell? An essential one cell is a one cell that is contained in only one prime implicant. So after we identify the prime implicants in step 1, we identify all of the essential one cells in step 2. In step 3, we identify all essential prime implicants. And an essential prime implicant is simply a prime implicant containing an essential one cell. And after that, the fourth step is to finish and find all minimal sums remember that each minimal sum must contain all of the essential prime implicants. Then add any other prime implicants that are needed. And once again, I definitely don't expect you to understand even a single one of these steps at this point. But after we've done a number of examples, I think that you'll find that this procedure is not too terribly difficult, and will be relatively easy to do. So let's start off with one of the problems in your book. We'll look at problem 5.3a, and you're supposed to find all minimal sums of products. So find all minimal sums of the function f1 of a, b, c is equal to little m0 plus little m2 plus little m5 plus little m6. So we have min term 0, min term 2, min term 5, and min term 6. And we want to write that function as compactly as possible. Now keep in mind that each one of these min terms has all three variables in it. So if we wrote out this function, now it's not necessary to do this, but I just want to make a point here. If we wrote out this function in algebraic notation, okay, each one of these min terms will have a, b, and c in it. So I'll go ahead and write a, b, c, a, b, c, a, b, c, and a, b, c. Now m0, well, remember 0 is 0, 0, 0, 2 is 0, 0, 1, 0, 5 is 1, 0, 1, and 6 is 1, 1, 0. And therefore, this first term corresponding to the 0, 0, 0 min term is a prime, b prime, c prime. For the next one, we have a prime, b, c prime. For the next one, a, b prime, c. and finally a, b, c prime. So this is the function f in algebraic notation, and we say that this has 12 literals because we have 3 variables in each of the 4 terms, and so 12 literal appearances of the variables. And we want to now use the Karnaugh map to write that function more compactly. So let's proceed. As usual, now we begin by noting that this is a function of 3 variables, and therefore the Karnaugh map will have 2 to the 3rd power, or 8 cells. So we go ahead and prepare the Karnaugh map, and we'll put A on the vertical axis and B and C on the horizontal axis, and as before, we'll remember the correct way to number the different cells. We have 0 and 1 on the vertical axis, and then on the horizontal axis 0, 0, 0, 1, 1, 1, and 1, 0. And now the most convenient way to fill in the Karnaugh map is to go back up here to the decimal notation, because we can pick them out real easily. The 0th midterm, remember, will be this one, and remember how we count. We go 0, 1, 2, 3, 4, 5, 6, and 7. So after 0, we see we have 2. 0, 1, 2. So we need to put a 1 here. Then the next one after 2 is 5. Okay? 0, 1, 2, 3, 4, 5. So we get a 1 here. And 6 is the last one. And remember, on the bottom row we go 4, 5, and then 6 and 7. So 6 will go over here in this position. So there's our Karnaugh map, and now we're ready to begin with these rules or the guidelines that were just outlined to see how this goes. Now we're supposed to remember, look for rectangular groupings of 1 cells. Now and we're supposed to start with the biggest possible groupings. Well, the biggest possible grouping, since we have altogether 8 cells, if we had all 1s here, that would be all one big grouping. But in fact, of our 8 cells, we don't have 8 1 cells, so there's no way to find a grouping of 8 1 cells. And so now we go down to the next lower power of 2. Remember, 8 is at 2 to the 3rd power. Now we'll go down to 2 to the 2nd power. What about 4? Well, indeed we do have 4 1 cells in this Karnaugh map, but they are not in a rectangular grouping. And therefore, we just conclude that we have no rectangular groupings of 4 1 cells. So now we go down to the next lowest power of 2, which is 2 to the 1st power, or 2. Now, do we have any rectangular groupings of 2 1 cells? And the answer is that we do. Now, I don't expect you to even see them this first time necessarily, so I'll show you, but in subsequent problems I'll give you a chance to look first before I help you. But in this case, we have the obvious grouping of these 2 1 cells, and you notice that this is a rectangular grouping right here. It's 2 adjacent 1 cells, and we have these 2 together form a rectangle. Now, if you look at this, you might not see any other groupings, but you need to remember as we stressed before, the top edge of the Karnaugh map is to be thought of as joining the bottom edge of the Karnaugh map, and the right edge of the Karnaugh map must be thought of as joining the left edge of the Karnaugh map. So we actually do have another grouping, and that is the grouping of this one cell with this one cell. That makes another possible grouping of two one cells. Now, let me comment carefully on what we have here. Notice that this second grouping that we've put down here, that we've identified, does overlap with the first grouping that we had. So you might hesitate and think that it is not allowed. However, the important thing to note here is that this second grouping is not entirely contained within the first grouping. If you identify a grouping at any point in this process, if you identify a grouping that is entirely contained within another grouping, you don't count it as a grouping. It doesn't count as a prime implicant. But if it merely overlaps with an existing grouping and has some of its one cells inside an existing grouping and some outside that pre-existing grouping, that's okay. And so that's why in this case we can go ahead and use this second grouping. Now, I personally like to keep a list of the prime implicants that I identify. And now we get to the next part of this, which is a little bit tricky, and that is trying to figure out what the names are for these prime implicants. Let's start with the first one we identified. Notice that that first one, recall that it is this vertical collection of the last two cells here at the extreme right of the Karnaugh map. And now we're trying to find out what the name is of this prime implicant. And let me tell you that when you're looking for the name of a prime implicant, you should always look for the variables that are constant in the prime implicant. Any variable that is changing in the prime implicant will not appear in the name. The only variables that appear in the name are those that are constant. So for instance, what do I mean by all that? Well, this prime implicant here, this first one that we identified, notice that in the top cell, A is equal to 0. In the bottom cell, A is equal to 1. Since A is changing within that prime implicant, its name will not appear, that variable A will not appear in the name of this prime implicant. However, B and C are both constant. They both stay constant. B stays constant and equal to 1. C stays constant and equal to 0. And so those two variables will be in the name. And since B is equal to 1 and C is equal to 0, this prime implicant is the prime implicant B, C prime. Now, you don't need to do this, but I like to actually, when I identify prime implicants, I like to just draw a little picture that helps me remember which prime implicant I've just identified. And so, again, you won't find this in the book, and it's not necessary for you to do it, but I like to do it because you'll see in this problem it's not too important, but in later problems where we have functions with many prime implicants, I find it helpful to be able to look at these little pictures. I think you'll see later what I mean. So anyway, the picture for this first prime implicant is the first prime implicant is BC prime, and here's the picture for it. Now let's try to identify the second prime implicant that we had, and that was the one that contains, in fact we can go ahead and draw the picture here, the one that contains this one cell and this one cell. Now you might think for a moment and ask yourself, well, what variable is changing? And the answer is the variable B. Notice that in this one cell, B is equal to 0, and in this one cell B is equal to 1. So since B is changing, it will not appear in the name for this prime implicant. However, A is constant and equal to 0 in these two cells. C is constant and equal to 0. So the name of this prime implicant is A prime C prime. Now, we look to see one last time, are there any other prime implicants with two one cells? And the answer is no. So now we move down to prime implicants with one cell, and now we can't include anything that is entirely contained within a pre-existing prime implicant. So for instance, here is a single one cell, but it is already contained within A prime C prime, so we can't count it. Likewise, this one's actually contained within two existing prime implicants, so we can't count it, and this is counted within the existing prime implicant BC prime, so we can't count it as a prime implicant. However, this one cell is not contained within any pre-existing prime implicant, and therefore we do count it. So I'll draw the picture, and I'll just put a circle there corresponding to this, and now we need to find a name for that. And since of course, since it's just one cell, no variable is changing, and therefore all three variables will appear in the name. And finally, since A is 1 and B is 0 and C is 1, this is A B prime C. So now we have listed all of the prime implicants in this problem. And that concludes steps 1 and 2. Now we need to figure out which of these prime implicants are essential prime implicants. And remember, an essential prime implicant is one that contains an essential one cell. And what is an essential one cell? It is a one cell that is contained within only one prime implicant. So let's go back up to the Karnaugh map, and we'll put an asterisk in every essential one cell that we observe. So let's start maybe with this one at the upper left hand corner, and we ask, is this one cell an essential one cell? And the answer is yes, because it is contained only within the prime implicant A prime C prime. It is not contained within any of our other prime implicants, and therefore this is an essential one cell. Let's move over to this one at the upper right hand corner. Is this one cell essential? And the answer this time is no. This cell is contained within two of our prime implicants. It's contained within BC prime, but it's also contained within A prime C prime. So this is not an essential one cell. Now let's go to the next row. What about this? Is this contained within only one prime implicant? And the answer is yes. It's only contained in the prime implicant A, B prime C. So this is an essential one cell. And finally, if we look at the lower right-hand corner, is this an essential one cell? And the answer is, again, yes. It is only contained within BC prime. So this is an essential one cell. And now we can decide what the essential prime implicants are. Remember, essential prime implicants are prime implicants that contain at least one essential one cell. Our first prime implicant, BC prime, is the one over here, and if we look up at the map, yes, it does contain an essential one cell. So BC prime is an essential prime implicant. What about A prime C prime? Well, it contains this one cell in the upper left hand corner. this essential one cell in the upper left-hand corner. So it is indeed essential. And finally, if we check the prime implicant A, B prime C, it contains this essential one cell, and therefore it is also essential. And so now we're ready to complete this problem. Now, I'll put minimal sum, and then after the word sum, I'll put S, because some functions have more than one minimal sum. That is, they have several different ways that are equally compact, or several different ways of writing them as sum that are equally compact, and some functions have only one minimal sum. And we'll see which is the case here. So we have F, that was, yes, F1 of ABC equals. Now, it is really crucial to note that every minimal sum must contain all of the essential prime implicants. Just think of the word essential means that they are essential. They are absolutely, they must be included. And then after you have what's essential, you'll add anything else that you need to add. So you'll see what I mean right now. So the essential prime implicants are B, C prime, and then OR that with A prime, C prime, and OR that with A, B prime, C. Now, how do we figure out if we need anything else? Well, what we do, what I like to do, is to go up to the Karnaugh map now, and we check what we have so far, BC prime. Now we remember right here, BC prime are these two cells on the extreme right side of the Karnaugh map. So that means that by including BC prime in my expression, I have accounted for those two cells. So I'll shade them in. Now, the next one, A prime, C prime. By including that in my sum, I have accounted for this cell at the upper left-hand corner, and also the cell over here in the upper right-hand corner, but it's already shaded, so I don't need to shade it again. And finally, by including A, B prime, C, remember that's this cell right here, so now I have accounted for this cell. So now I ask myself, are there any more cells that need to be accounted for? And the answer is no, and therefore I am done. And this is our final answer. Now, sometimes after you have written down all the essential the essential prime implicants, you'll still have some other cells that need to be accounted for, and then we might have several different options. But in this case, once we accounted for all the essential prime implicants, there were no more cells that needed to be considered. So this is our answer. There's only one minimal sum in this case. And notice that we do have a significant savings. Here in our first expression, we had 12 literals. And in this expression, we have 1, 2, 3, 4, 5, 6, 7 literals. So you can think of this in the following way. One reason that this is a practical thing to do is that if we wanted to do this in hardware, if we wanted to realize it, we would need 4 3-input AND gates and 1 4-input OR gate. But here we would need just 1 3-input OR gate and 2 2-input AND gates and 1 3-input AND gate to implement this in hardware. So this is one of the reasons that we want to learn this procedure for finding minimal sums and then later minimal products. So that's our first example, our first complete example of how to use a Karnaugh map. So now let's move on to another example. We have 5.3c. Maybe we should do B first. B is a little bit simpler, and then we'll go to C. So let's go to 5.3b. And in this one, we have F2 of D, E, F is equal to the sum of the min terms 0, 1, 2, and 4. And we want to, again, find all minimal sums. Now, by the way, before I go to this problem, I would like to suggest that you do one last thing. I have simply stated here that this expression that we derived, this expression right here, I said that it is a valid expression for F1, which we have up here. I strongly encourage you to try to verify that that is true. In other words, okay, here you have an expression for F1, and up here you have the min-term expansion for F1. You should know now how to take any expression for a function and find the min-term expansion of the function. In this case, it would be very easy. You just need to AND the first term with A or A prime, and the second term with B or B prime, and then eliminate any redundancies, and you'll get the min-term expansion. So I strongly encourage you to try that and to verify that if you do that, this expression here will yield back this min-term expansion, which will prove to you that this expression here really is equal to the same function F1 that we started with up here. Again, I strongly encourage you to do that. But now, for this new problem, again, if we wished, we could go ahead and write out this function in algebraic form. I want to stress that it's not necessary to do that unless you want to check your work, or unless you just want to really show the viewer the savings that is occurring from simplification. So this is not necessary, but again, I'll show it here. So we'll have F2 of D, E, F equals, and we see that we have 4 min terms, and of course each min term must have all 3 variables. So we'll have D, E, F, D, E, F, D, E, F, and D, E, F. 0 is 0, 0, 0, 1 is 0, 0, 1, 2 is 0, 1, 0, and 4 is 1, 0, 0. So we get the first term is D prime, E prime, F prime, D prime, E prime, F, D prime, E, F prime, and finally D, E prime, F prime. So as was the case in the previous problem, we have 12 literals, and let's see how much simplification we'll have this time. Once again, we have a function with 3 variables, and so we'll have a Karnaugh map with 2 to the 3rd, or 8 cells. the first variable is D, so we'll put that on the vertical axis. E and F are the second and third variables, so we'll put those on the horizontal axis. We'll use our usual way of numbering the Karnaugh map. And now once again, as was the case before, when we actually want to put the ones in the Karnaugh map, it's easiest to go back here to the decimal notation and to recall again 0, 1, 2, 3, 4, 5, 6, 7. So 0 is this first cell, 1, 2, we don't have 3, but we do have 4. And that will be the Karnaugh map for the function f2. And now let's go through our steps again. Once again, remember, first step is to find the prime implicants. Okay, we have a total of 8 cells. Do we have any groupings of 8 one cells? Certainly not, because there are only 4 one cells present. So no groupings of 8 one cells. Let's go down to the next power of 2, which is 4. Do we have any rectangular groupings of 4 one cells? The answer again is no. We do have 4 one cells here, but they don't fall in a rectangular grouping. Now notice, let me just make sure you understand how they could. If this one right here, if instead of being right there, it were right here in this position, or well, let's say that if this one right here were in this position, then this would be a grouping, a rectangular grouping of 4 one cells. Or if this one right here were instead up here, then the entire top row would be a grouping, a rectangular grouping of 4 one cells. But in this case, with the distribution of one cells like this that we see here, we don't have a rectangular grouping of 4. So now we drop down to the next power of 2, which is 2. And now when we're looking for groupings of 2 one cells, we have several options. Now, I like to suggest to students, and this is not hugely important, but I'll suggest to students that when they have a number of options, they always start with the option that is the hardest to see, so that they don't forget it later. And so that's what I'll do now. When I look at this Karnaugh map, I see that one grouping of 2 one cells that's sort of tricky to see is this one. There are several groupings of 2 one cells, but that one is the one I think is the trickiest to see, and therefore I'll take it first. So I'm going to go ahead and draw my picture. And when you do these pictures, certainly don't take, if you even choose to do the pictures as I do, don't take much time with them. They don't need to be perfect drawings. They just need to help you remember what prime implicants are where. So I'll draw that rough picture, and now I need to figure out the name for that prime implicant. And I hope that you will see that D is constant in that prime implicant, so it will appear in the name. But E is not constant. E is equal to 0 in this cell on the left, and E is equal to 1 in this cell on the right. So E will not appear in the name, but F is constant and equal to 0. So D is constant and equal to 0, F is constant and equal to 0, so this is D prime F prime. And that's one prime implicant of size 2. Now, I don't see any more prime implicants of size 2 that are tricky, so let's do the ones that are obvious. And the first one that's obvious is this one. And again, notice it is not, although it does overlap with a prime implicant we already have, it's not entirely contained within it, so that's okay. I'll draw the rough figure for this one. And now you might take a moment to see if you can name it yourself and then come back. When I now try to name it, I observe that the value of D is changing. It's equal to 0 in the top cell and 1 in the bottom cell. And therefore D will not be part of this prime implicant. However, E and F are both constant, and in fact both are equal to 0. So this is E prime F prime. And now I look at the Karnaugh map again, and I see that there's another grouping of 2 1 cells, and it is this one. And again, that's not, although it does overlap our 2 previous prime implicants, it's not entirely contained within either one, and therefore we need to have it. And so we now draw the rough figure for it, and let's you should now turn off the video for a moment and try to figure out the name of that prime implicant. Well, as I look at that, I see that D is constant equal to 0, so that means that since D is constant, it will be in the name, and since D is equal to 0, it'll be D prime. I see that E is also constant in those 2 cells and equal to 0, so we'll have E prime. F, however, is changing. It's equal to 0 in this cell on the left, right here, and F is equal to 1 in this cell, and so since F is changing, it will not appear in the name. Now, having done this, I see no more groupings of 2 1 cells, and so now I move down to the next level. Are there any groupings of 1 1 cell? Well, there are certainly 1 cells, there are single 1 cells, but none that are not already contained within one of the prime implicants we've already identified, and therefore we're done. These 3 prime implicants that we have identified are the only prime implicants for this problem. So now we need to ask ourselves, what are the essential prime implicants? And to find the essential prime implicants, remember that the procedure here is to begin by finding the essential 1 cells. Is this 1 cell essential? Clearly not, because in fact it's contained within all 3 of our existing prime implicants. And remember, to be essential, a 1 cell must be contained within only 1 prime implicant. So this 1 cell is not essential. However, this one is, so we'll put an asterisk here. And this one is essential, so we put an asterisk here. And finally, this one is also essential, so we put an asterisk there. Now that we've identified the essential 1 cells, we know that the essential prime implicants are prime implicants that contain an essential 1 cell. So let's ask about the first one. Is it essential? Yes, because it contains this essential 1 cell here in the upper right hand corner. So D prime F prime is essential. What about E prime F prime? Yes, it contains this essential 1 cell, so it is essential. And what about D prime E prime? Well, it contains this essential 1 cell, so it is also essential. And now we move, as we did before, to the minimal sums. And so the function name here is F2. We have F2 of D, E, F. And remember, we always start with what is essential. So we must put down D prime F prime, or E prime F prime, or D prime E prime. And now we want to see if anything else is needed. And so let's look at what we've accounted for first. D prime F prime. By including D prime F prime in our minimal sum, we have taken care of this one cell and this one cell. You can see now maybe why the figures are a little convenient to have. By including E prime F prime, we have looked at, we've considered these two one cells. And by considering D prime E prime, we have these two one cells. And so now we ask the question, are there any remaining cells that we've not accounted for? And the answer is no. And therefore, as in the previous case, we have only one minimal sum. And it is this. And in this case, you see that there are 6 literals. So we've gone from an expression for F2 containing 12 literals to an expression containing 6 literals. And once again, I encourage you to take this expression that we've just found, find the min-term expansion for it, and you will find that it matches what we have here at the top. So these expressions are equivalent. However, this is of course, a much more compact way of writing the function F2. Let's have one more example in this lecture. We'll go back to one we were going to do earlier, which is 5.3b. C. So in this function, in this case, we have F3 of R, S, T is equal to R, T prime, or R prime, S prime, or R prime S. And we notice that that has 6 literals. And our job, once again, is to find all minimal sums. This is a function of 3 variables, so we will have 2 to the 3rd power cells in our Karnaugh map, or 8. We'll have R on the vertical axis and S and T on the horizontal axis. Number this as usual. Now, this one is just a little bit trickier to fill in because we don't have a min-term expansion here, but I believe that we'll be able to do this as long as we're patient. So let's look at the first term, R T prime. Well, first of all, since we have an R rather than an R prime, we know that we're going to be in the second row of the Karnaugh map because that's where R is equal to 1. And T prime means that T is equal to 0. Now T is if we look up above, T is the second number, so we're going to get a 1 here and a 1 here. And notice that if you looked at those two cells as a grouping, you would notice that S is changing, so S would not appear in the name, but R is constant for those two cells, T is constant for those two cells, R is constant equal to 1, T is constant equal to 0, so indeed the name would be RT prime. Now, having seen that, I hope that you can fill in the rest of the ones for the rest of the term, so I encourage you to stop the video now, try to fill in the Karnaugh map for the remaining terms, and then we'll look at these together. Okay, I hope you had good luck with that, and so now let's finish this up. R prime, S prime. Since we have R prime, we know we're on the top row of the Karnaugh map, and S prime says that S is equal to 0, so we have this one and this one. Notice that R is 0 and S is 0, but T is changing, and so T is not in the name. And finally, R prime S means that we have R is equal to 0 and S is equal to 1, which gives us those two ones right there. Now now that we have the Karnaugh map for this function, we're ready to do this problem. So, as usual, the first step is to find the prime implicants. We have a problem with 8 cells, so we first ask, are there any rectangular groupings of 8 one cells? And the answer is certainly no, because we only have 6 one cells present. So let's go down now to groupings of 4 one cells. Well, indeed, there are rectangular groupings of 4 one cells here. And I feel very confident you see one for sure, and it is the 4 ones at the top of the Karnaugh map. But there is another grouping of 4 one cells, and you need to another rectangular grouping of 4 one cells, and you need to be aware of it. So since it's a trickier one, I'll handle it first. We can group together these 4 one cells, those 2 one cells, with these 2 one cells, if we remember that the right and left edges of the Karnaugh map are connected, and that will give us a grouping, a rectangular grouping of 4 one cells. So that's one that's easy to miss, and you want to make sure not to miss it. So there it is. And now we need to ask ourselves, what is the name for this prime implicant? Well, does it have an R in it? No. R is equal to 0 along for the top 2 cells and 1 for the bottom 2 cells, so R is not in the name. What about S? S is equal to 0 for these 2 cells, and it's equal to 1 for these 2 cells, so since S is changing, it's not in the name either. But what about T? T is equal to 0 for these 2 cells, and T is equal to 0 for these 2 cells. So in fact, the name of this prime implicant is simply T prime. And we have one more grouping of 4 one cells, and that's the obvious one here along the top. And what will be the name of this? Well, if you check those 4 cells along the top, you see that S is changing and T is changing, but R is constant equal to 0. So this is R prime.